All right, let's do paper one. So, question one in paper one is a question about the gradients of chords. Gradients is just slopes, and we have the points for all of these chords. So you can see in my working there, to find the slope of CE, I just use the points from C to E, E being my ending point, C being my starting point, and I plug the points in. To find DE, same thing, plugged in the points from D to E and got solutions. All right, now hopefully the thing that you notice here is that A, B, C, and D are all getting closer and closer to E. So as we get closer and closer, we can sort of see a trend of what's happening with the slope here from 4 to 3 to 2.5 to 2.1, which would probably lead us to believe that the slope of the tangent when we get to that point is going to be 2. All right, number 2. We're given 2 functions in there. And the first thing, there's 2 things we got to find here. One, we need to figure out what g of f of x is. We find that by plugging f of x into g of x. And then we also need to find the inverse of f. The way we find the inverse of f is to like switch the x and the y and then solve for the y. So that's the way that I found out what the inverse of f was. And then to find g of f of x, I just took the f function and plugged it into the g function and simplified it down. All right, so then I've got those 2 things. I set them equal to each other, and then I solve those down. If at any point in here I'm going too fast, just pause the video and look through the work. And then if you have questions later on, send me an email. All right, so we've got an arithmetic progression. So we have formulas for those. They're on the formula. They're on your Pure Math formula sheet. One of the formulas is that any term, the value of any term in an arithmetic progression, is equal to the first term plus the common difference times the number term that it is minus 1. So if I was trying to find the 50th term, right, a sub 50, I would do 7 plus whatever the common difference is between the terms times 49. All right, so it gives us a couple of pieces of information in here. It tells us that the nth term is 84. All right, so this, whatever term equals 84, we don't know which term that is yet. That's equal to 7 plus the common difference times n minus 1. And it tells us that the 3nth term is equal to 245. So whatever term equals 245, that's equal to 7 plus d times 3n minus 1. All right, now it's just the simultaneous equations. So we solve this one down to here. We get 77 plus d equals dn. And then here, I could solve this one down to 237 minus 3dn equals d. I substituted then this 77 plus d in for dn right here, because then I could solve straight for d. So remember what d is the common difference in this case, which means this arithmetic progression is going up by 3.5 each time. So down here, I wrote the way that this progression starts. So it goes 7, then 10.5, then 14, 17.5, 21, so on and so forth. All right, so that's how I figured out what d was. I plugged that back into my equation to figure out what n was, and I got the n was 23. So in this case, that 84 is the 23rd term, which seems pretty reasonable if this is the first term, and it's going up by 7 every 2 terms. That by the 23rd term, I would be up to 84. Okay, so number 4 is one where we're given the derivative and we have to find the original function. So we're finding the antiderivative here. I think it's always useful when we're finding derivatives or antiderivatives to think about all these exponents not in fraction form. So that's why I rewrote everything like this, because it's then easier to think through, okay, I've got to raise the exponent by 1. So this is going to have to go from negative 1/2 up to positive 1/2. And then if I think through what would the derivative of this have been, it would have, so my first guess at it would have been this one, x plus 6 to the 1/2. But if I did that derivative, it would have ended up being 1/2 x plus 6 to the 1/2. And I don't need a 1/2 when I do the derivative, so I've got to multiply the front by 2 to get rid of that. This one's pretty easy to do. We've got to go, this has to go up by 1, so it's going to be negative 1. The derivative of this would switch the sign, so I need to make this negative 6. And then there's some constant on the end, and we don't know what that is yet. The way we figure out what that is to go to this, and we know that f of 3 equals 1. So we plug in 3 for x, and we plug in 1 for f of x, and then we just solve it down for what my constant is, and that tells me that this was my equation. All right, part 5, or number 5. Okay, so this translation means that what I want the x, every x to be shifted 2 to the right. And remember that the way I accomplish that in a function is anywhere that there's an x, I write x minus 2. Okay, and that's just a principle of doing shifts to graphs. So some basic ones are like to shift left and right. You replace every x with an x plus something to move it to the left, and you replace it with an x minus something to move it to the right. If you want to shift it up and down, just on the very back side, you put a plus however much you want it to move up, or a minus however much you want it to move down. You, if you want something to be vertically stretched, you multiply this whole thing, you multiply any x by a certain amount, and vice versa if you want it to be horizontally stretched. Those are things you should have covered last year. If you don't remember those and you want some practice on that, get in touch with me, and I think I can probably hook you up with something, either another video or something on Khan Academy that you can work through. Anyway, so every x just gets replaced with an x minus 2. When we simplify that down algebraically, we get to that quadratic. All right, part B discusses what are the things, like what happens when you change this to this. So when you multiply everything in the function by a certain amount, that creates a vertical stretch. So everything here is getting 3 times as big along the y-axis, right? So what if this was a 1 before, it becomes 3. If this was a 5 before, it's now 15. So it's getting stretched up vertically. The other change is that this went from x to negative x. What that's going to do is just flip everything over the over the y-axis, because all the positive x's have now turned into negative x's. Anything that was at point 2 before is now at negative 2. All right, so 6 is a binomial expansion. So the thing to remember for binomial expansions is that every term, as we expand it out, has really three parts to it. So this first part here is Pascal's triangle. And you'll notice down here at the bottom, I did Pascal's triangle down to the sixth row, just so I can see what my terms are going to be. If these were just an x and a y, so if there were no coefficients in either of these, then these would be the coefficients of my terms as I expanded this out. Because these have coefficients in them already, I need to multiply those coefficients by these to get what that ending coefficient is. All right, so the first part is Pascal's triangle. All right, the second term always comes from taking this thing and starting it to this power and then working its way down. So this will start at the sixth power, and the next term is to the fifth power, and the next term to the fourth power, third, second, all the way down to zero. And then the third part comes from taking this term and starting it at the zero power and working your way up to this number. So this starts at the zero power and then goes to the one power, would go squared, all the way up to 6. Now notice, these exponents are always going to add up to this number. 6 plus 0 is 6, 5 plus 1 is 6, so on and so forth. Okay, so we want the terms that end up being, so on the top here, I just wrote what the first two terms would be if you did this whole expansion. Now, this would then keep going. So you could do the whole expansion, see where things ended up, any place where you had an x squared or an x cubed. Okay, or we can shortcut this and just use the parts of this that are going to give us an x squared and an x cubed. That's pretty easy because we have just an x right here. So the only times where this is going to end up being x squared or x cubed is where this last term here, the one with the caret underneath, ends up as x squared or x cubed. So that's these two terms. All right, so 2 to the fourth negative x squared, that's going to give me an x squared. And then this 2 to the third negative x cubed, that's going to give me the x cubed. All right, then it's just a question of expanding all these things out. So the second term in here, so this is 6 choose 2 is a way to do this. If you can put that in your calculator, if you have this little button, this NCR, you can put in a 6 and then that button and then a 2, and it will tell you that that is this one down here, the 15, right? So it's the 0, 1, 2, 3, 4, 5, 6 term. Okay, so 15, and then 2 to the fourth is 16, negative x all squared is x squared. 6 choose 3 is 20, 2 to the third is 8, negative x all cubed is negative x cubed, and then it's just simplifying those down to get that part. Okay, for part B, we want to figure out what is the coefficient of x cubed when we do this expansion. Okay, so in this case, we've got a 3 to the x that's going to get multiplied in, and we've got a 1 that's going to get multiplied in. So what things in that case are going to give me an x cubed? So the places where that will happen is when I have to multiply the 3x times something that has the x squared in it, or when I'm doing the 1 times the thing that has the x cubed in it. We got these from part A of the question. All right, those are from there. So when I multiply this 3x by 240x squared, I get 720x cubed. 1 times negative 160x cubed is negative 160x cubed. Add those together and you get 560x cubed. And so the coefficient is 560. Question 7 is a trig identities question. And in this case, it's just a matter of plugging in identities until you can turn one thing into the other thing. So we are turning this whole equation into this. Now, the first thing to notice is that this tangent can be written as sine over cosine. When you simplify that down, you get this whole thing here. Now, the thing I noticed from this is that I want to get rid of my fraction. So I'm going to multiply this whole equation, both sides of it, by cosine x. When I do that, I get cosine x plus sine squared x plus 5 cosine squared x. All right, I'm almost to the point where I've gotten rid of everything that's not cosine. Remember, I want to get to a point where everything's cosine. I need this to turn into a cosine. And remember, sine squared and cosine squared can change into each other. Just do one minus the other. So sine squared x is equal to 1 minus cosine squared x. And when you plug that in there and move everything over to the right side, you get the equation that you were trying to turn this into. All right, part B. It says, hence, solve that equation. Remember, whenever it says hence, it means don't solve this equation. Solve using the thing you just showed that this equals. So immediately I rewrite this as that and then solve that equation. The key here is to notice that this is a quadratic. So I changed it to a quadratic. I factored it down. I got the roots for this as 1/2 or negative 1/3. When I then substitute back, so cosine of x equals 1/2 or negative 1/3. So if I do cosine of 1/2, I get 60 degrees. Remember, we're doing cosine, so you got to think of it's not only this, but it would be 360 minus that. So it equals 60 degrees or 300 degrees from this one. However, our domain is only from 0 to 180. So the 300 I'm not going to include from this one. For the negative, when cosine equals negative 1/3, that happens at 109.5. Again, I need to do 360 minus that, but when I do that, it's going to be bigger than 180, so it's going to be outside the domain. So that's the two answers that I get for that trig problem. All right, in 8a, we're just taking a derivative, and the key to these always is to rewrite the fraction with the negative exponent. And this is going to require you to do chain rule. So taking the exponent down, -2 times this stuff in the parentheses to the -2. And then because of chain rule, I got to multiply that by the derivative of this stuff, which is -2. Simplifying that all down, -12 times -2 is 24. And then moving this down to the denominator to make it a positive exponent. Okay, so for part B is almost should remind you a little bit of parametric equations. So the thing to remember here is we have what dy dx is, and dy dx is always equal to dy dt over dx dt, or an easier way to think about it in this case, it's equal to dy dt times dt over dx, so those would cancel out, right? So dy dt, I think it gave it to us, right? Yes, it gave it to us. It's 0.4 units per second. And then it told us that dx dt, so the x coordinate is changing at 0.15. So I did it this way just so I could plug the fractions in pretty easily. So 2/5 times 20/3 equals 8/3. Another way, I mean, you can also think of this as dy dt over dx dt. And in this case, that might be easier because you got a 0.4 over 0.15, right? Or 40 over 15, which is also going to equal 8 over 3. All right, and then, it asks us to find the possible x-coordinates of A. So then what we need to do then is set that derivative equal to 8/3 and then solve it down. So if we cross multiply both sides here, we get 72 equals 8 times all this stuff, or 9 equals that stuff. And if I then solve that down to get these two separate equations, then x either equals 0 or x equals 3. All right, question 9 is there are easy parts to it, and the second part's really hard, but I've seen this come up on many specimen papers and on a lot of paper ones, this sort of overlapping circle question. The first part I think is pretty easy. It tells us that circle A, the little circle, has a radius of r. And then it wants us to show that BC has a radius of r root 2. Well, the key to that is seeing that this is r, so is this. And that's our right triangle. So r squared plus r squared is going to equal bc squared. And that's where this comes from. Add those two together, you get 2r squared. Take the square root of 2r squared, and you get r root 2. All right, that part's pretty easy. All right, finding the area of the shaded region. Okay, so the area of the shaded region, basically, you need to take half of circle A and then take out this part. Okay, so there's a lot of parts we need to find here, and like remembering which area you're working on at any time can be difficult. But the key thing is we want to find how big is the semicircle of circle A, and then we want to try to take out this like chunk right there, that like arc CAD part. Okay, well, to find this part, what we need to do is find the area of this whole sector right here. Okay, and then take out this triangle. All right, well, fortunately, finding this part isn't that difficult because this is a quarter of circle B. So if we can take a quarter of circle B and then take out this triangle right here, triangle CBD, then I'll be left with this area right there. Okay, so let's step through all this stuff. Okay. All right, so that triangle there, first of all, is 1/2 times 2r times r. So up here, the base of that triangle is 2r, there's r, so the area of that triangle is r squared. All right, the area of that like pie piece, that quarter of circle B is exactly this, 1/4 of circle B. And that ends up being just 1/2 pi r squared. All right, so the area of that shaded segment, the way I'm noting that here is this CAD, this part, is just this minus that. Okay, so it leaves me with this. The area of that semicircle of circle A is 1/2 pi r squared because the radius of circle A is r. All right, so the area of the shaded region is going to be this minus this. And when we do the algebra on that, you see that this part just cancels with this part. When I distribute the negative in, this becomes positive, so we just end up with r squared. There's no like difficult algebra on there. It's conceptually thinking through how do I make that shaded area. All right, so question 10, we need to rewrite this equation in the equation for a circle. So in order to have the equation of a circle, I need to have it in this form right here. And to get in this form, we have to complete the square. So here's how I completed the square. I moved the x's together and the y's together, and then I left a blank. All right? And the thing I'm putting in the blank here is the thing that's going to make this a perfect square. And the way I figure out what that is I take this thing, I cut it in half, and then I square it. So 4 divided by 2 is 2. 2 squared is 4. All right, to make up for the fact that I'm adding 4 to this equation right here, I've got to subtract 4 right here. Okay, I did the same thing for the y's. Took this, divided by 2, that gives me negative 1. Negative 1 squared is 1. To make up for the fact that I'm adding 1 right here, I got to subtract 1 out here. All right, this becomes this. X plus 2 squared will FOIL out to that. Y minus 1 squared will FOIL out to that. These all added together are negative 25. When I move them over here, it's a positive 25. The center of this circle is at negative 2, comma 1, and the radius is 5. All right. Now, for this part, the key for part B is recognizing that point D is going to be, if I can figure out the slope of CD, so from the center to D, if I can figure out the slope of that, the slope of AB has to be perpendicular to that. And the reason for that is that anytime you have a circle, any 2 points that are on the circle, if I connect a chord with them, and then I go from the center to the midpoint of that, it's going to be perpendicular. So the slope of CD, so from C to D, to find the slope, I just plugged in the points of that, and I got a slope of 1/7. Because AB and CD are perpendicular, the slope of AB has to be -7, negative reciprocal of 1/7. And then to write the equation, it's y equals -7x plus b, and I know it goes through the point 1.5, 1.5. I use that to figure out what my intercept is. It's 12, so there's the equation of my line. Okay, so then to figure out the coordinates of A and B, what I did was just did substitution. So y equals -7x plus 12, I know that A and B are both on that line, and I know that they're both on this circle. So I just plugged this in here for y. All right, and it took a fair bit of algebra to get to that point. But fortunately, once you get to here, you can factor out a 50. It's not a terribly complex quadratic at that point. You get that x equals 1 and 2. And then you can get the y values by plugging those back into the equation for the line. Okay, question 11 is another completing the square question. So you can see that it's a quadratic, so you know that it's either it's gonna be a parabola, either opening up or down. We want to put it in vertex form so that we can see where the min or max is. And then here is just me completing the square. I need this thing behind this to be a 9. 6 divided by 2 is 3. 3 squared is 9. To make up for adding 9 here, I got to subtract 9 out here. So here is f of x written in vertex form. The vertex of this parabola is at -3, -17. And because this is positive, right, or even looking up here, you can see that x squared is positive. You know that it opens up. So you know that this is a minimum point of the parabola. So the range is that f has to be greater than or equal to -17, or y has to be greater than or equal to 17. That's how you write what the range is. Then if you change it in part B to where a equals 5, and you're given the two roots, so you're given the roots of k and -2k. Basically, what I did there was just rewrote. So here is an equation that's going to have the roots k and -2k. I FOILed that out and got to this. Well, I know that that looks like this. It needs to look like this because I know that a is going to equal 5. I don't know what b is yet. All right, but if I look here, I know that whatever is right here, that has to equal 5. So that tells me that k equals 5. This whole thing here is equal to b, and I know that k is 5. So then if I just plug this in here, 5 squared is 25, times 2 is 50, and then it's negative. So b is -50. Okay, in part C, you want to show that if it has no real roots, then a squared has to be less than 4 times the quantity of b minus a. All right, so to rewrite the original equation, we just plug in x plus a everywhere that x is, and then set that equal to a. So that's takes a little bit of algebra. We're gonna write it. We got to FOIL this out. We got to multiply the a through here. We can do some simplification down to get it down to this point. Okay, and it might be kind of hard to see, but now this is a quadratic. All right, and in this quadratic, the thing in front of the x squared is just a 1. So for purposes of quadratic formula here, x equals 1. B is going to equal the coefficient of x, which is just 3a. And then c is all this junk back here, 2a squared plus b minus a. All right, so that gives me an a, a b, and a c. A quadratic has no real roots whenever the discriminant is less than 0. So all I really got to do here is set b squared minus 4ac less than 0. And then that's what I've done in the work down here. So there's b squared minus 4 times a times c, which is all that garbage. All right, doing some algebra on this and then simplifying it down, I can get down to the point where a squared is less than 4 times b minus a, which is what it wanted me to show in this problem. Okay, last problem. All right, so we got a lot of stuff going on here. We know that a is the minimum point, a comma 0. We know that b is at a maximum point. We need to show in the first part what the value of a is. Well, since we know that a is on the x-axis, we know the y-coordinate equals 0. So we just need to plug in, set the equation equal to 0. And if we do this and we solve that, right, either x would have to equal 0 or x would equal 2. Here is the point where it equals 0. So here's the point where it equals 2. So a is at 2. That is the easier way. You could also, because it's a minimum point, you could take the derivative of this and set it equal to 0, which we're going to have to do in a second anyway um, for part B. So for part B, if you FOIL all this out, which you don't have to do, you could do product rule here to do this, but I think it's probably easier to just FOIL this all out and then take a much simpler derivative. If you FOIL this out, distribute the x in, you get to this cubic expression, the derivative of which is this. You can factor that down to these two, so you get that x equals 2/3 and 2. This is this point up here, right? That's where the minimum was. We already found that. We could have done that up here to also find what the value of a was. But since we know that's that point, this has to be where b is, the maximum point, at 2/3. All right, asking for the area of the shaded region is the same as asking for the integral from 0 to 2 of that equation. We already FOILed that whole thing out a second ago. It's going to be much easier to do the antiderivative when we've got it written out as a long polynomial. So then it's just term by term finding the antiderivative. All right, so each of these, the exponent has to go up by 1, and then you need to put something here that's going to give you the right coefficient once you've done the derivative. Okay, we end up with this. We evaluate it from 0 to 2, so we plug 2 in to all of these first, and then we plug 0 into all of these, and then it's just a question of simplifying it down, and we get 4/3. Okay, all right. So the gradient of the curve has a minimum value m, and we want to figure out what is the value of m. So if we think of dy dx as telling us what the gradient is, we want to find, we've already found what that is. It's this, right? And we want to find when does this have a minimum value. So really what it's asking us to do is take the derivative of the derivative, or the second derivative. So when we take the derivative of this, we get that. If we set that equal to 0, we get that x equals 4/3. All right, we want to find out what that minimum value is, and so in order to do that, we need to plug that back into the dy dx. So we plug 4/3 back in here, and we get -4/3. That is what the minimum value of the gradient would be. And if you look back along here, right, the minimum value of the gradient, so the gradient, if my pencil is the tangent everywhere along here, those are all positive, 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 positive. It hits 0 right there, right? Then it's going to get more and more negative, and at some point it's going to turn back and get less negative until it hits 0, and then it's going to get positive again. So it's somewhere in here where it's going to hit its minimum value, right? It's going to be as negative as it gets, and it's somewhere along here it's -4/3, something that's just a little bit less than 1, or a little bit less than -1. And I think that's it. Okay, again, I know I went pretty fast through a lot of that. My hope is that what this video can do is help fill in some of the gaps as you looked through the work that I had already uploaded, in case you didn't see, hey, why did you write this step down? And hopefully this is going to answer some questions, but you're still going to have more questions. So please, please email me with them. You can post them on Canvas. If you think it's a question other people are going to benefit from, by all means, post it on Canvas so I can answer it on there. Let me know if things technologically aren't working. I am learning this as you guys are. Like, we're adjusting to a very new normal here, and I want to make it as helpful as I can. And in a lot of ways, I think this can be even better, and I think it gives us time to do a lot of work on our own and then be able to answer questions. As long as we're all making a good faith effort, I think we'll be fine. If you have any other questions about grades or anything like that, please email me. I'm on email every day. You can expect something back within a day. Stay safe.